So now let's get to the next problem. Problem number 3.169. So this problem says when the pump in figure 3.169 draws 220 meter cube per hour. So this is the pump, and it flows a water flow rate 220 meter cube per hour of water at 20 degrees Celsius from the reservoir. So basically, this is the reservoir. Sorry. The total friction head loss is 5 meter. Friction head loss, is 5 meter. So that's the loss, actually, loss of water, loss of energy. Now, so this friction head loss, meaning, once, when you flow water or anything through a pipe, in this pipe, you have some friction, right? So you have some energy loss, and that's the amount is 5 meter friction head loss. And the flow discharges through a nozzle. So basically, this is the nozzle to the atmosphere. Estimate the pump power in kilowatt. So we need to calculate the pump power in kilowatt, right? Now delivered to the water. So to solve this problem, basically, we will assume that this is the surface of reservoir. Let's assume this is condition 1, right? Position 1, and the outlet of the nozzle is 2. Okay, then we will just balance the energy equation at point 1 and point 2. That should be enough. Now, before we balance out, let's go to the next slide. Okay, so yeah. What is the draw? Okay. Okay. So okay. So now if we apply steady flow energy equation at point 1 and point 2, you see that the point 1 position, you will have a pressure, pressure P1 by rho z plus, at this condition, you have the kinetic energy V1 square by 2z plus you have the positional energy, which is the Z1, equals to, at position 2, you have the same, all these parameters same, right? Similar. P2 by rho z plus, at this condition, position V2 square by 2z plus Z2. Now, we also need to add 2 more things. One is the, you see the frictional loss head, so which is the HF, that should be added in the second part. And we are adding energy using this pump, right? So that should be negative. You see the loss is positive, and the pump energy that is actually applied or added to the fluid is negative, because we are adding it to the right side. Okay, now you see that at position 1, if we assume that there is no any pressure, or P1 equals to 0, so that means the P2 at position P2 will also be 0, because both of them are in atmospheric pressure, right? And then so this will be 0, this will be 0, right? V1 square. Now at position 1, we assume that the reservoir fluid is in stagnant condition, or it's in unmoving condition. There is no movement of water, right? There is no velocity of water in this position. So if the velocity is water is 0, that means that's also 0. And the Z1. So this Z1, if we assume that this is the baseline, Z1 is 0, then we can calculate the Z2. Z2 is basically the distance between these 2 points, right? So it should be the 2. You see, the Z2 is just the 2. Now, for here, we still need to calculate the V2 square by 2z, right? Now, we don't know the V2, what is the velocity of water at this condition, but we have the flow rate. So we can calculate the velocity at position 2. using the same equation, V2 equals to Q by A2. Now Q equals to 220 meter cube per hour. So to convert it to meter cube by second, we just need to divide it. 220 by 3600. That should be the meter cube per second. Now for the area, A is basically pi r square, right? Now pi is pi and r. Here we are given the d, 5 centimeter. So if we divide it by 2, we will get the radius. So that is 2.5 centimeter. Now if we divide it by 100, that should be meter. That means 0.025. You see the 0.025 meters square. Now if we calculate this, this will be the velocity at condition P2 position, right? So we can input this value, you see v square by 2z. So 2 multiplied 9.81 and v is 31.12 square. Now this is the frictional loss, HF, right? Frictional head loss, that is 2, is given in the equation question. Now this is the power of the pump. So that's what we need to calculate. So you get the horsepower equals to 56.4 meter. So that's the head power, right? Now in the question, it asks to calculate the power of the pump in horsepower condition, right? So to calculate it in horsepower, we can use this equation: P equals to rho Z Q. So P rho equals 998, Z equals to 9.81, and Q equals to Q is given here actually 220 by 3600. Basically, we converted this meter cube per hour to meter cube per second, and the H equals to 56.4. You see the HP or H equals to 56.4. Now, if we calculate this, we should get 3,700 watt, and we divide it by 1,000, we get the kilowatt in unit, right? 33.7 kilowatt. So that's the answer for this question.